Hello guys, welcome back to another episode of Power Logic. So today I'm gonna be live solving the 2021 USA JMO problem 1, which asks that let this be a set of positive integers, find all functions that such that the input is natural number and output is also natural number, such that for all positive integers a and b, this is equal to f of a, f of b, and f of a squared is equal to f of a squared. So we can use induction and recursion by finding the first few terms. So f of 1 is pretty trivial. F of 1 is just equal to 1, right? Yeah. Because f of 1 square, no, f of 1 square, so just f of 1. F of 1 is equal to f of 1 square. And since that is always going to be a natural number, then f of 1 is going to be equal to 1. F of 2 is kind of clear. It's equal to f of 1 square plus f of 1 square. Which is equal by using this first rule, it becomes f of 1 times f of 1, which is equal to 1. And f of 3, it becomes kind of unclear because you cannot directly put numbers inside. But we can use the Pythagorean triple. Using the fact that f of 3 square so we can use the fact that f of 3 square plus 4 square is equal to f of 5 square, which is equal to f of 5, which is equal to f of 2 square plus 1 square. No, which is, so f of 5 square is equal to f of 5 square. So it's equal to f of 5 entire thing square, which becomes f of 2 square plus 1 square. Sorry, this line is incorrect. This becomes f of 2 square plus 1 square, which clearly is equal to 1. And f of 6 is equal to, well, f of 6 is equal to, we can use the same trick. Okay, so we know that f of 3 and f of 4 are all equal to 1. So now f of 6 is equal to f of, so we can say that f of 6, so f of 6 squared plus f of a squared is equal to f of 10 squared plus a squared is equal to f of 3 squared times f of, so f of 3 times f of 1 squared. Well, entire thing. Which, because this is f of 6 times f of 8 and they are both natural numbers, then f of 6, 8 are all equal to 1. And while f of 9 is also equal to 1. Because f of 9 is equal to f of 3 squared, which is equal to f of 3 squared, which is equal to 1, because we know that f of 3 is equal to 1. So now, it's time for the induction. So, it'll be kind of, it starts to become clear that we can write this as f of a squared. So the Pythagorean triple works like this, right? So you have a squared minus b squared, 2ab, and a squared plus b squared is a Pythagorean triple. So we can see that like this, that a squared minus b squared plus, yeah, so this basically is f of a squared minus b squared f of 2ab equals to f of is equal to f of a squared plus b squared, which is equal to f of ab. And we know that f of a comma f of b is equal to 1, then these two are always going to be equal to 1. So what can we get from this? So we know all the way from 1 to n, then n squared is equal to 1. The f of n squared is equal to 1, and we know that f of 1 to f of n is odd. So we know that if f of 1 to f of 9 is all equal to 1. Yeah, so what can we do now? So so now we can see that if we know f of 1 to f of n, they are all equal to 1. Like f of 1 to f of 9, right? So f of 7 is basically because f of 25 is equal to 1, then f of 24 and f of 1 are equal to 1. Yeah. So and we know that f of 1 to f of n is equal to 1, then f of n squared is clearly equal to 1. And how about, and then f of n plus 1 is equal to what? So n plus 1 squared is equal to n squared plus 1 squared plus, no, n squared plus 2n plus 1. Yeah, the f of n plus 1 is always going to be equal to, so if it's a Pythagorean triple, then n plus 1 squared, the n is equal to a squared, right? Then n minus 1 square 2n, n plus 1 is a Pythagorean triple? But yeah, so, no, so n minus 1, 2n, and n plus 1 is a Pythagorean triple. Wait, what? Wait, no. So we know f of 1 to f of n, and we want to find f of n plus 1. N plus 1 is basically, so that Wait, how will I say 2n? So 2n is equal to, wait, so I think we can set this basically equal to 2n. So if we know that from f of 1 to f of 2n is equal to 1, then obviously f of 4n squared is equal to 1 because it's a square. But I don't think this is too necessary. So if we know that f of 1 to f of 2n is equal to 1, then f of 2n plus 1 is equal to, wait, fn plus 1. Okay, yeah. So f of n plus 1 is equal to f of n plus 1 square minus n square. Which we know that n plus 1 and r. So which we know that, this becomes f of, wait, no. So 2n plus 1 is equal to the difference of these two. Which basically gives us the induction that f of 2n, then f of 2n plus 1, f of n square is equal to f of n plus 1 square. The whole thing is square. And since we know that this is equal to 1, then these two are both equal to 1, right? Yeah, so I think we're kind of close, but so we know that, yeah, we also have to prove that, yeah, is this done? F of 2n plus 1. So we know f of 1 to f of 2n, then that this is done. This is done. No, so if we know that from f of 1 to f of 2n plus 1, then 2n plus, no, so we want to also prove that f of 2n from f of 1 to f of 2n plus 1, then f of 2n plus 2 is equal to 1, right? So n minus 1 squared. So yeah, I think this is pretty complete for the induction. So are we done? F of 2n plus 1 is equal to f of n minus plus 1 squared. So how about if you know f of 2n plus 1? Wait, then f of 2n plus 2. Then f of 2n plus 2. So f of 2n plus 2 is equal to this thing plus 1 square. So we know 2n plus 1, then so want to find now we just want to find f of 2n plus 2, and that's basically done. So wait. So we can write this as difference of square, then this is gonna work. So f of 1 to f of 2, and then f of 2n plus 1. F of 2n plus 2. So that these two are equal to 1, right? N square. So just want to find the induction of 2n plus 2. And yeah, so f of a squared is equal to f of a inheritance squared by the rule, and f of a squared plus b squared is equal to f of a times f of b. Right. I cannot really make it n plus 1 squared minus is equal to f of 2 times n plus 1. Like if we know f of 8, right, we know that from a f of 1 to f of 8 and f of 16. Oh, just f of 8, f of 18. And yeah, so if n plus 1 can be expressed as a and b, which is equal to f of 2 times n plus 1. And let's say if n plus 1 can be expressed as a times b, then the a squared minus b squared, a squared plus b squared, and the thing. And this can always be expressed as n plus 1. And even if n plus 1 can be expressed as a prime number, then n plus 1 can be always expressed as a square. No, n plus 1 can be expressed as just a times 1. Even if like this, then a square minus 1 square. Then a square. So even if this is the smallest case, then a square minus 1 square, a square plus 1 square, and 2n plus 1. It's gonna be a triple. No, so if this is n plus 1 times 1, then n plus 1 square minus 1 square. No, wait. So even if n square, n plus 1s can be expressed as n plus 1 times 1, then n plus 1, then n plus 1 square minus 1 square, n plus 1 square minus n square. It's basically equal to n squared plus 2n. Then n plus, so n squared plus 2n, n squared plus 2n plus 2. No, so basically n squared, n plus 1 square minus 1 square. No, n plus 1 square minus 1, n plus 1 square plus 1, and n plus, and 2n plus 1 is a Pythagorean triple. Then 2n plus 1. So we'll just know that n plus 1 square plus 1 square is a. So if f of n square, so if f of n plus 1 square plus 1 square is equal to. So the induction basically becomes like this. So we can say that if f of n plus 1 square plus 1 square is equal to 1, then these two are all equal to 1, right? So now I think this basically become completed because we know that, so we multiply these two together, right? And both of them we know that since from 1 to 2n is all equal to 1, then these two must be equal to 1. So 1 times 1 is equal to 1. So because these two are all natural numbers, then they are all equal to 1. So this basically completes our proof because from 2n plus 3n, because from 2n plus 3 and so on, then the cycle will be like going through this back and forth, right? Since you know that f1 f of 1 to f of 2n plus 2, which is f of 2 times n plus 1 is equal to 1, then this plus 1 is always going to go through this rule, right? Thank you for watching. Have a great day and see you next time.